Hey, so today we're going to look at some applications of electron configuration. So hopefully at this point you're feeling a little bit more comfortable with electron configurations and using the periodic table to create those notations which describe the location of the electrons within the atom. So first thing that I want to point out and show everyone is there is a shorthand. So when we get further on in the periodic table, some things have 60, 70, 80 electrons, and we have to describe the location of those. And that can be a little tiresome and tedious. And at the end of the day, really, we just need to know what the outermost or valence electrons are doing. And so the gas shorthand is a cool trick. So what we're going to do for this is we're going to write the noble gas in brackets, then continue the electron configuration afterwards. So let me show you why this kind of works. So if we're looking at argon and potassium, so argon is the element right before potassium on the periodic table. And you can see that the electron configuration for argon is almost the same as potassium. In fact, we have right here to right here, it's exactly the same. So potassium has the same electron configuration as argon, plus this one extra electron, and that one extra electron is now in the 4s subshell. So what we can go ahead and do is we can go ahead and say, hey, all right, cool. So potassium has the electron configuration of argon. So you write argon in brackets like such, and you literally just continue the electron configuration afterwards, 4s1. And that is a perfectly acceptable way to write an electron configuration for a chemical. You can write them for any chemical. You can either write the complete or the noble gas shorthand, and you are A-OK for identifying the location of the atom's electrons. Now, quantum numbers are getting a little bit more specific into how we are describing the electron's position within atoms. The quantum numbers are a set of 4 numbers that specifically describe the location, orientation, and spin of the electron. And that's going to be like the new hot topic that we're going to be kind of thinking about. Now, the Pauli exclusion principle basically states that it's impossible for an electron to have the same set of quantum numbers within an element. Now, this is interesting because basically it's saying that it's impossible for an electron to behave in the exact same way as another electron. Even if an electron is within the same atom, within the same shell and subshell, energy level or sublevel, they would have to have opposite spins. So in order for 2 electrons to be in the same orbital, same sublevel, because we know we can have 2 electrons per orbital, they must have opposite spins. And all that really does for us is it gives us a little bit of magnetic information about the electrons, and that's perfectly fine for our level of chemistry. And in terms of quantum numbers, we denote those positive 1/2 and negative 1/2. But at the end of the day, that's really all you need to know about quantum numbers. They're a set of numbers that describe the location and orientation. In order for 2 electrons to be in the same orbital or same subshell, they have to have opposite spins, and you're in the clear for that. So an orbital notation is basically a description, a drawing for showing the electron's spin and orbital location within an atom. And it really just kind of gives us information about the valence shell electrons. But let me go ahead and show you how to draw the orbital notation first. We're going to go ahead and look at oxygen. So oxygen's electron configuration is 1s2, 2s2, 2p4. And what we're going to go ahead and do is we're going to represent each one of these subshells, with the electrons as arrows and the orbitals as boxes or lines. It kind of depends on how you want to do it. So let's first look at the 1s subshell. So we know that for every energy level, there is 1s orbital. So we're going to go ahead and label this as 1s. And it tells us that there are 2 electrons. There are 2 electrons in this 1s orbital. Now remember, in order for 2 electrons to be in the same orbital, and there's only 1 orbital here, they have to have opposite spin. So we're going to say that one of the electrons is spin up and the other electron is spin down. We have the next set of orbitals here, the 2s electrons. So we're going to go ahead and say, hey, all right, we know that for every energy level, there's one s orbital, and so that's going to be the 2s orbital. And there are also two electrons within this orbital. One's going to be spin up, the other is going to be spin down. So we have an arrow up and an arrow down. And then last but not least, we know that for the 2p sublevels, there's going to be there's three orbitals. So we're going to go ahead and draw three orbitals, three 2p orbitals per energy level. So as far as this goes, I have 4 electrons, which I need to go ahead and like orientate and put into these orbitals. And if you're kind of paying attention, there's a couple ways you can do this. We can go like one here, one here, and one here. And notice that I went ahead and drew these all up. And then that last electron, I've drawn 3 and there's 4. That last electron can technically go into any one of these orbitals, but by convention, we usually go from left to right, filling these up, and then this last one's going to go down. So that is the way you fill these orbitals, but I do want to point out, like, I could have done something along the lines of this, where I did one up and one down. Now, that is not good. This is not the way you would draw an orbital notation for oxygen, and the reason that is because it kind of leaves this last orbital empty. Remember, electrons are negatively charged. So if you have 2 electrons, you're going to want to put one of those electrons into each one of those orbitals. Last but not least, I do want to point out that I could have done like one up, one down, one up. And electrons don't fill orbitals this way. They always fill orbitals with the same spin before pairing up with opposite spin electrons. So you always do up, 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 down, 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 or you could do down, 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 up, up, up. But as long as they're all the same. So the orbital notation for oxygen is going to be like this, where you have up, 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 and then one last electron down. Now, the information that this kind of tells us is it tells us the number of unpaired electrons that oxygen has. Notice that there are 2 electrons that are unpaired. So these are 2 unpaired electrons. Looks like all of oxygen's orbitals are occupied. And that's some of the language that we would use for this. So Hund's rule. Hund's rule states that electrons fill all degenerate orbitals with the same spin before pairing. So this is kind of what I was saying before, where you go up, 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 down, down, down. Notice that the one on the left is the correct way of drawing the orbital notation for, would this be carbon, because there's 6 electrons, and the one on the right would be the incorrect. The word degenerate just means equal in energy or same energy. So each one of these p orbitals here, there are 3 p orbitals, are degenerate with each other. They are equal in energy. So there are 3 degenerate orbital. And once again, down below, we have the example for carbon. And then last but not least, valence and core electrons. We've talked about these probably a good amount in our class so far, but just a reminder that valence electrons are defined as the outermost electrons. So when we're looking at this, the outermost electrons are going to, goodness gracious me, am I? The outermost electrons are going to be the electrons that are in the 3rd energy level, because the way we define distance from the nucleus and outermost is the energy level. Remember, energy level is the distance from the nucleus. So the electrons that are in the 3rd energy level are furthest away from the nucleus. So this example here is one of aluminum. Aluminum has 3 valence electrons, and anything that isn't in those outermost shells are going to be core electrons. So it has 10 core electrons. All right, cool. Now, what we're going to go ahead and transition into here is basically describing valence electrons and the orbital notation. Let me go ahead and clear my drawings here. Once again, kind of establishing some vocabulary, we can have paired or unpaired electrons. So if I were to look at lithium, the electron configuration for lithium is 1s2, 2s1. Notice the 2 electrons in the 1s subshell are paired. They have opposite spins, so we draw them spin up and spin down, whereas the electron in the 2s subshell is unpaired. It doesn't have a partner. All right, so what we're going to do is transition here and talk really like about a very important experimental setup in the world of chemistry, and that is photoelectron spectroscopy, abbreviated PES for short. And what this is a device which is used to help determine the element's electron configuration. And you have to be very comfortable representing or reading these graphs which represent the electron configurations. If you're comfortable with writing electron configurations, these graphs are actually not too bad to interpret. So for example, let's go ahead and look at nitrogen. So this is the photoelectron spectrum data for nitrogen. And what I want to start off with is just, let's remind ourselves what the electron configuration for nitrogen is. Nitrogen has 7 electrons. It has 1s2, 2 electrons in that first energy level. It has 2 electrons in that second energy level, sublevel, and then 3 electrons in the 2p sublevel. So 2, 4, and then 7. So there are our 7 electrons. And interestingly enough, the graph below represents this electron configuration. What I want to point out are a couple things. First, I want to point out the axes. So the y-axis here is the number of electrons, and the x-axis is the energy. As you can see, the 2 peaks here are fairly close to each other, and then this first peak is fairly far away. And if you kind of read the electron configuration, you can almost map it onto the photoelectron spectrum data. So if you can see, this first peak here is representative of the 1s peak. The second one is going to be the 2s peak, and then the third one is going to be the 2p peak. And what's even more awesome, more crazy, is that it seems that every 2 lines represents an electron. Every 2 scratches here is a electron, and as we can see, the relative number of electrons in the 1s peak is 2, the relative number of electrons in the 2s peak is 2, and the relative number of electrons in the 2p peak is 3. So these graphs here, if you kind of have a grasp, on electron configurations, are not terrible. Let's go ahead and check out the photoelectron spectrum data for sodium. So sodium, the electron configuration is going to be, sorry about that, is going to be 1s2, 2s2, 2p6, 3s1. And once again, you can kind of go ahead and map onto our graph here each one of these peaks in order of energy. 3s, and it seems that each one of these lines is representative of an electron, the relative number of electrons. 2, 3, 4, 5, 6, and then 1. So it's really nice. You can actually kind of see what the electron configuration is based off of this graph. Now, before moving on, I do want to point out one thing here. I do want to point out the location of, draw here, the 1s peak. So it seems to me that the sodium's 1s peak is at about 100, usually it's like kilojoules per mole. So this peak here is listed at 100, whereas sodium's 1s peak, sodium's 1s peak is at about, I don't know, 50 or 60. Why would sodium's 1s peak be further to the left? Well, what we're doing is we're looking at ionization data for these electrons. We're basically looking at how much energy it takes to remove the electrons from each one of these respective subshells. So if you have electrons in the 1s shell for nitrogen, versus electrons in the 1s shell for sodium, the electrons in the 1s shell for sodium are going to be significantly harder to remove. And the reason that is because the sodium atom has more protons. And because it has more protons, there's a more positive charge within the nucleus. And that positive charge is effectively better at attracting electrons that are in the same subshell. So the 1s peak for sodium is further to the left, or has a greater number than nitrogen does, because it has more protons. What I want you to go ahead and do is try to identify what this last element is, and you are good to go. So thank you so much, and you know where to find me if you have any questions. Awesome. Bye.